Hello guys, my name is Dehou and my partner is Anifat. Today we want to introduce the adaptive self-sufficient item set miner for transactional data streams. In my presentation, I will go through the introduction, the concept, and the adaptive self-sufficient item set miner which proposed by the authors, and the experiment evaluation, the contributions of the paper, then end up with the future works. So as we know, there are some drawbacks when we are using the association rule mining. Um, you may end up with some spurious frequent patterns which contains values that appears together by chance, but they don't have really strong correlations, which means those kind of frequent patterns is not valuable to us. Uh, the second drawback is that when we are dealing with the data stream, uh, there's always some new transactions arriving. So those new transactions may potentially change the underlying data distribution over time of the whole data set. This is also known as the concept drift. I will talk about this concept drifts in more details in the coming slides. So the motivation of this paper is that they want to propose a framework or algorithm that can solve the data stream mining. They want to mining the self-sufficient item set, while meanwhile they want to solve the concept drift problem. So what is the data stream? The data stream is basically a sequence of data that arrives continuously. Uh, the whole data set is dynamic and they have unbounded insights and they're generating at a very fast pace. This is very intuitive that you just have a sequence of dynamic data set arriving in a timely manner. The self-sufficient item sets is the item set that have a frequency that is significantly different from the frequency of their subset and their superset. So this is a very general definitions. There are some more details about this self-sufficient item set has been details in the paper. In the paper in this paper, the author has like given out a very detailed explanation about what is the self-sufficient item set and how why they are important and why we should mining this self-sufficient item set. And there's a one important statement they made is that the self-sufficient item set is more valuable to the data analyst than the frequent item set. So in this paper, they are focusing on mining the self-sufficient item set rather than the frequent item set. The regional concept drift is that when you have a data stream, when there is some new transaction arriving, they will change the underlying data distribution over time. So, for example, let's say if you have a transaction database for a supermarket, and at some time point, the supplier of the Pepsi told you that he will not going to supply the Pepsi to this supermarket anymore. So after this time point, all the frequent items that you have that contains the Pepsi will not be interesting to you anymore because we know that in the future there will be no Pepsi in this supermarket. So if you have some frequent item set that based on the past data that contains the Pepsi as items in the frequent item set, then those item sets are not valuable anymore. So this is an example of the regional concept drift, which means that the new transaction may make some influence about the past transactions. So this kind of problem can also make the machine learning model inaccurate because there is some inconsistency between the existing data and the new data. So now I want to talk about the adaptive self-sufficient item set manner, as known as the ASSIM. This is a framework that this paper proposed to solve the problem we have mentioned before. Uh, so in this picture, it gives a very general idea about the structures of the ASSIM and how the data flows inside ASSIM. So so we have our data set in the left side, and this data set will go through the batch size calculator. The batch size calculator will um, divide all those streaming data in groups, and for each of the batches, they will enter the self-sufficient item set generator. This generator will basically give you the potential self-sufficient item set, and for each of those item set, they will go through the regional concept drift adapter (RCDA). This adapter will check each single self-sufficient item set to see if there is a concept drift happens. If a concept drift is happen, then it will decide to let the self-sufficient item generator to regenerate new item set, or um, they will just ignore that item set. So in the end, we will get a self-sufficient item set. We will get all the self-sufficient item set as our result. So first, let's talk about the batch processing. The batch size calculator is the first part of our ASSM framework. So it will handle the frequency counting and the batch size calculations. It will ensure that a proper stable batch size was used before we mine for the self-sufficient item set. If the batch size is too small, the variance of the item set may be an issue, and also if our batch size is too large, then it will gives us a very large delay or lag. So to get a proper batch size is very important for us to process in the next step. The SSIG, basically it will check for all the potential interesting patterns and generate all the potential self-sufficient item set. It will have multiple tests to check if all those item set can pass a test, and if a item set can pass all those constraints or all those tests, then it will consider that item set to be a self-sufficient item set. Then it will pass this item set in the next step, which is the uh, RCDA. So RCDA will uh, it is actually a concept drift detector. It will detect all the concept drifts for each of the self-sufficient item set coming from the SSIG. It will analyze those concept drift and decide like where and when to remine additional items using the SSIG. Then in the end, we will have all the self-sufficient item sets. Now, we want to talk about the experiment evaluation. This paper did three groups of the testing. The first group is that they want to know the computational cost of our algorithm. They are measuring the runtime and the memory performance. The second test is that they want to know the accuracy of our ASSIM. they use precision and recall to do the to beat the matrix. And the third test is that they want to know the efficiency and accuracy of our drift detector. So this is all the data set that we have. Most of them are coming from reliable sources, and they are well used in most of the area. The first test is that they want to measure the runtime and the memory performance. If you look at this SSIG without batches, this is a group of uh, data that they are using as the ground truth because there's no batches. They just treat all, the whole data set as a static data set and just give out like all then just mining to for all the self-sufficient atom set, then use those atoms as the ground truth. The remaining three groups, the first one is the ASSIM, which is our proposed algorithm. This one is the SSIG with the fixed intervals. It just divided into the same amount of the batches as the BSC, but in a fixed interval. This group is SSG with batches. Uh, in this group, they have predetermined predetermined size of the interval founding using the BSC. Uh, in in this group, they are using the BSD first to find the size of the interval and just apply those interval to our SSIG. So as you can see that in our proposed ASSM, the time is lesser than all of the three groups, and but it requires a little more memory. But it requires more memory. But in general, it is acceptable. It's not a huge memory consumption. You just need more memories. The second group is the accuracy uh, test. There we're using. You can see here the ASSM has a better precision and also better recall uh, than other two groups, which means the ASSM may be a better choice to do the can solve the uh, can solve our problem pretty well. The third one is the third test is to test how efficiency and accuracy of our drift detector. Uh, there are two. They have considered two kind of drift. The first one is the abrupt. This kind of drift is that the means the drift happens uh, suddenly, just and it will uh, change all the stuff. And the second one is the gradual, means the drift happens very slowly and is that kind of very uh, in a gradual manner. So as you can see here, they both have 100% true positive, but uh, in abrupt drift, when the number of drifts goes higher, the false positive goes higher, and in the uh, gradual drift detection, you can find same stuff. When the slope gets higher, the false positive gets higher, and get we also have a higher delay. So this paper has give us AS framework or called ASSM to do the streaming data mining. So it will basically you can handle the work. It can um, return all the uh, self-sufficient asset, and it can also handle the concept drift problem pretty well. In the future, we may want to develop a more accurate method for uh, concept drift adapter to handle a better uh, real world data streams. So thank you guys. So time for the questions.